Hi, this is Andrea Legrand, and today we are in my bedroom for looking at a conical tank. So that means we have a different radius at the top than we have at the bottom. And so we're going to be looking at the process of changing the height within the tank. So when we have a flow rate going in and flow rate going out, the height of the liquid in the tank is going to fluctuate. Okay, so let's start with some basics. So when we look at volume, we have the integral from 0 to some height of the cross-sectional area dH. Yeah? So from that, you can also write this as dV over dt is equal to cross-sectional area change of height over time. Yes. All right. So when we look at this, we can add in another way to look at the change of volume over time, which is dV over dt is equal to the flow rate in minus the flow rate out. Okay, so that's where we're going to start. Now, the other way we can also look at this, we can look at it through Bernoulli's equation and look at the volume coming out, right? So with Bernoulli's, we have V out is equal to V squared over 2, which is also equal to gas constant times height. Okay? When we combine this one and this one, we get, I'm going to just do double arrows there, we get dV over dt is equal to the flow rate in minus the square root of 2gh. So with this, we also have to take into consideration the area of the hole, right? So what we're going to do is we're going to add that buddy right here. All right. Now we can maneuver this around, and it's kind of getting cramped, I'm sorry, on my screen. But we take this and we can make it so that it's a reference of the change of height over time. So that would be the cross-sectional area, dH over dt, is equal to Qn minus AH square root 2GH. And then we can manipulate this around to give us just our dH over dt. So we have dH over dt is equal to Qn minus AH square root 2GH all over AC. So I just erased what we had before and moved this up. So this is our final equation. And now when we continue looking at this, we obviously need to find our Qn, right? So our Qn is based off of, when you manipulate everything, ends up being equal to AH to GH. And so we need it to be our initial height, because height is ever changing, it's based off time. So we look at it as H naught, or H when time is equal to 0, is equal to the flow rate in initial over our AH square root of 2G. Everything is squared, which ends up just being Qn naught squared over AH squared times 2G, because cancels out the radical. So when we look at this from this point of view, we can throw that in and you get that Qn is equal to AH square root of 2G, and then I'm going to pull out that H naught and put it to the 1/2. So technically it's under that radical, but I like putting it out here so that it's easier to, incorporate it all. Cool. So now we have two different radiuses, right? So we have a radius at the top and a radius at the bottom. And when we look at the height, so the height, let's make a little graph. we have our radius at the top, and we have our radius at the bottom, because the radius at the bottom isn't zero, and the height at the bottom isn't zero, okay, because there is some variation. So we have all the way over here is our H total. So that's the highest height that we can have, right? So when we look at this, it's going to be something like this, and pretend like that's a straight line. I'm not great at drawing straight lines. I can't even walk in a straight line. So it is a linear expression. When we put in algebra to look at our radius depending on the height, we get our radius is equal to our top minus our bottom over our height total, and then we got to add in our height at the time, and then minus our bottom, because our bottom is not zero. It is a value, so we're given our bottom at the beginning of our equation, and so we take this and then we're going to move it over into Google Collaboratory and code it. We're going to take what we just did and code it in Python, aka Google Collaboratory. Now, I know that my setup's kind of weird. Ordered a camera, didn't come in time, so I'm kind of making do with what I can. So here's a lovely mirror behind me, so you can kind of see what I'm doing. I'm going to try to keep my body like angled this way, so that you can see what I am doing. So I apologize for that. And then just so you know, uh, which way is easier for me to lean? This way. There's my whiteboard right there. It just has uh, our equation on it, our dv over dt equation, which we did in the video earlier, and then that our inlet flow increased by 20%. So that's just basically our initial conditions, and also me wanting to make sure that I don't mess up the signs, which I did, FYI, in our calculation for R. I said minus R bottom, it's actually plus R bottom, that's my bad. I don't know why I said that, but you add the R bottom because that's the initial condition. You don't subtract it. If it was like a change, then yeah, but my bad. I take ownership, but at least I fixed it now. So let's get started. All right, so this is my second take of coding because I realized that I did not set up my oops, sorry, let me fix that. I did not set up my screen recording. So I recorded myself talking without showing you what I was doing. So here I am again. Let's do this. So let me double check that I've got everything. Okay. I don't want to do this a third time. Okay. So I did some preemptive coding. So here is us importing all of our basic code. So we have NumPy, basic calculations, we have subplots, making sure that we can graph it, and then we have integration, solve IVP. So then I put in our initial values. So our whole cross-sectional area is 0.01 meters cubed. We have our gravitational constant, our Qn, so our initial Qn is 0.1 meters cubed per second. Then we have our initial height, which I calculated for you guys earlier, where you pull it all out, and then, yeah. And so I put that in, so I don't have to worry about it later. Then our radius at the bottom is 1 meter. Our radius at the top is 5. And then we have our total height, so that's the highest that the tank can go. Doesn't mean that it can't overflow, but that's so we know what our limit is. And then RT, which is the time, so how many run-throughs are we going to do? How many seconds are we going to have this graph go for? So let's start. So we have to start with defining our tank area. So we're going to go def, I'm going to call this tank because it makes life easier. I'm going to come back to that, make sure I get everything all together. So this is where we're going to put in our radius equation. Again, if I'm looking over here, it's because I have it written down, corrected, so it's a plus, not a minus. So we have r is equal to, we have r underscore top minus r bot. And then we multiply that by our height, close parentheses, divide it by our height total, and then we add, not subtract, our bottom. All right, and so from that we have our top, we have our bottom, we have h, and we have our total. All right, so we have that, and then we want it to return the area at that height. So we go return, it is np.pi, so that's how we get our pi function, multiplied by r squared classic area. All right, shift enter, all good, cool. All right, so now we're going to put in our, I'm going to call this LVL, so I look at this as our fluid level. So we are basing for our fluid level. All right, so as I stated before, we're looking at this so that our flow rate is increasing by 20% from our initial. So that means that we have to multiply our initial Q value by 1.2 because there's 100% and then we're adding an additional 20, so 1.2. So we have our Q in is equal to 1.2 times Q in naught. All right, and then, can you enter? Thank you. All right, so now we're going to put in our AC. So our AC is going to be, basically, we're going to run this formula that we just made. All right, and I'm just copying and pasting it to make my life easier, less chance for mistakes. All right, and so what are we going to return? We are going to return our dV over dt equation that we went in. So again, if I'm looking over here, it's because I have it written down. It is, we are returning it in the form of an array. So np.array. Make sure we have our brackets. And then we have q in minus ah times, we have our 2gh to the power of 0.5 because it's under a radical, and then divide it all by AC. Whoop. And then shift enter. Cool, cool. All right, and so now we have to do our integrating because remember that was dV over dt. So that is where we add in our solve IVP. So I'm going to call this res because this is our result, and I like having 3 letters and not more because I don't know, it just makes me happy. So we're going to have res, we go solve underscore IVP, and then we have our parentheses, so we're going to do LVL. We're going to go 0 to t, and then we have our np.array, and we have to put in, make sure it's in brackets, 0. Oh, I need to go back and put in my variables. I will do that before I press shift enter. We do np array, and then we have to do our dense output underscore outputs. Oh, that was, I need an underscore. Thank you very much. If I can spell, that'd be great. Okay, cool. And that is equal to true. And then I'm going to come back here and put in all my stuff. So we just need for this just T and I believe just T and H. Cool. All right. So now that we have that, we have to get ready to make our plot. So we have to set up what our T plot's going to look like. So I'm going to call that T plot. And that is lin space times, we're going to go 0, we're going to run it T times, so that's our 5,000. And then we're going to go about 100 gaps. So like it's going to go through by hundreds. All right. And then we also need to add in H, which is going to be, yeah. So our H is going to be our res dot sol, so our result solution. And then we're going to do T, and then we only want the first value, so we're going to put 0 in the array. Shift enter. Nope. Oh, np dot linspace. Whoopsies. Np dot shift enter. Cool. All right, now it's time to graph. Okay, so we need a graph, which means we got to put in all of our plotly stuff. So fig is equal to make underscore subplots. And we're going to leave just the parentheses. So that's just making sure that we don't have to put make subplots every single time. And then we're going to do fig dot add underscore scatter. And then we have to do our x and y values. So our x values is going to be our t plot. So that's our time variable. And then our y axis is going to be our height. And then shift enter. No, you don't like it. Okay, so I found it. Instead of t, it's t plot because I didn't define it. So right now it was trying to basically do the graph, but with not the first value for t plot. It's like, yeah, there we go. Okay, so if you look at this, oh, I put an extra 0 in there. Whoopsies. I gotta shift enter on all of these. Cool. So we see a slight curve, and so that means it's gradually gonna start tapering off. So that's what we want because it starts reaching as close to equilibrium as possible. All right, so let's add some more seconds. So let's go to 10,000 and see if we can see when it's evening out, and it's not yet. So we're going to up it a little bit more, and we got to go to, I don't want 50, ooh, too much. We're going to do 50,000. Oh, wait, sorry, 0. There we go. So if you see it's starting to level off, so that's showing it's slowly reaching equilibrium, and this is good because it is below 7.5. So based off the way the graph is, this would be where 7.5 is. And so that means we're not overflowing the tank. So we're good. All right, so that was how we code this. And then I will see you guys for the 3 tank problem.